Hello, everyone, and welcome to today's lecture. Today, we're going to actually be talking about, I guess, a special topic within software quality, but something that's getting more and more prevalence in terms of its importance uh, I would say, in almost every industry. And that's the topic of security. So security is just one aspect of quality, but it's an aspect that there's a lot of attention paid to. And you can understand that when you think about the fact that so much of today's software is dependent on large amounts of data. And often with that data, there becomes opportunities for people to want to exploit systems and obtain that data or obtain private information and so on that they might consider valuable. So what we're going to talk about today a little bit is the relationship between quality and security. And then what we're going to talk about is one particular example, which is a buffer overflow. And then what I want to do is talk about how we can test and analyze for security. So I'm going to talk about two things. I'm going to talk about testing for security and using static analysis. And static analysis isn't something we've covered yet in the course. We'll be doing a full lecture on it, but I just want to give you a little bit of an introduction to that. Lastly, what I want to do, because I committed to this at the beginning of the course, was I wanted to actually relate this to a practical case study. And I'm going to talk to you about cybersecurity in connected autonomous vehicles, specifically related to a large pan-European project that I've been involved in over the past 3 years that's just recently come to an end. So I'll talk a little bit about how we actually do the challenges, I guess, around cybersecurity in autonomous vehicles and one of the ways we can actually try to prevent them. So that's the plan for today. Any questions before we proceed? Okay, seeing no questions, we'll move on. One of the things I think when we think about quality and security is the relationship here, right? And um, when we talk about high quality software, which is one of the things we've talked about a lot in this course as a software quality assurance course, one of the questions that invariably comes up when you think about security is, does it when we say something is of high quality, does that also mean it's secure? Or should it mean it's secure? What do you think? Does high quality necessitate the need for secure? I'm seeing a lot of yeses in the chat. I see one not entirely. If you, generally, usually, yeah. And here's where I would say is that high quality software does equal secure software in the context of if the software requires. So I would expect that something that has to be secure would include requirements regarding the security specified up front. Um, so that is sort of my perspective on it. In general, I think that security should be designed into the software, right? Security is not just an afterthought. It should be something that you think about from day one. And that in general is the best approach, is to actually design with security in mind, not adapt a system to be secure later. So in that sense, yes. And I would say these two things are related. And quality in general includes many different dimensions. Quality can include functional correctness. It can include performance. It can include security, maintainability, interoperability, portability, testability, readability, a whole bunch of things. And in that respect, security is one aspect of quality and should be considered. So let's look at one example here just to kind of get a sense of what we're talking about. When I'm talking about security, what's one challenge or what's one example that can come about? How many of you have heard of a buffer overflow before? Someone says they have, you have. Um, did you hear about it in a course or just on your own or in the news, online, social media, course, all of the above, systems course, when you're learning to work with buffers? Okay. So basically, a buffer overflow is a type of security vulnerability that exists or that can exist in software systems, and it's caused by when you write data to a fixed size buffer, normally writing it to a stack or an array or something, but you actually write data that is longer than the fixed length. So, and where can this occur? Well, it turns out some languages are sort of you're kind of protected against this, but there are languages which are considered unsafe programming languages, meaning that they're not memory or type safe. For example, something like C++. And in these languages, the programmer, if they want something, if they want to protect against somebody writing too much data to a buffer, they need to explicitly protect against it. They need to check the length of the data coming in before they actually store it in the stack, before they store it in the array, etc. So the idea here is basically that buffer overflow can happen in an unsafe programming language when the programmer doesn't explicitly protect against it, and when the user tries to write more data into that buffer and essentially overflow it. And when somebody overflows a buffer, the consequences for this can be a number of things. It could be actually some unintended behavior in the software. It could actually cause the program itself to crash, throw an exception, or something else. But in general, what you're going to get is something unexpected happening in the sense of either unexpected behavior or in terms of the stability of the program. So that's an example of a buffer overflow. And when you think about it, is if I were actually designing my software to prevent buffer overflows, how could I go about doing that? If I'm you, what are some decisions I can make early on? So one of my requirements might be that we don't allow buffer overflow, so we protect against buffer overflows or something like that. So if we had something in our requirements around security, which referred to things like buffer overflows, what could we do early on? Well, any thoughts? We could have predefined buffer sizes. Okay, so we're going to have those buffer sizes, but there's a couple things we could do. One of them is we could actually make a decision around the language we choose and choose a safe programming language if we're flexible on the language, right? So that could be if we've got a choice between a couple of different language options based on the expertise in-house and the language that we need to support. We could choose one that is a safe programming language and therefore address the issue by sort of at the language level. The other thing is we can actually incorporate into our design requirements regarding data verification or validation. So you can validate that the data is actually of the appropriate length before it's actually stored. So you can actually add in to the design some safeguards to data input practices within the system. And that's one thing you could also do. And there are different ways of kind of doing that programmatically depending on the language and so on. But we could make these decisions ahead of time to account for this. Now, if we didn't account for buffer overflows and it became a problem later, what would we have to do? Well, what we would basically have to do is go back and sort of retrofit in a lot of checks, right? Because at the point where the software exists, we're not going to change the programming language. So we would have to go back and find all of the places in the code where we write to a fixed size buffer, and we'd have to build in checks to make sure that the buffer doesn't get written with data that's too large. So we'd have to go back and modify the code to essentially fix this vulnerability. Now, the challenge is if we had actually designed it in a way that accounted for this early on, it probably would be a lot easier. For example, we could actually redefine an input function that has built-in checking. It takes as a parameter the content and the length of the buffer and does a check first before it passes it on to be stored. versus we may have to now go and do this at every point independently, potentially, or something like that. It may actually be a more costly fix to do and retrofit later on in the code. So just keep that in mind. Any questions about buffer overflows? This course isn't about buffer overflows. I just bring it up so you have a sense of one particular challenge. Okay, so if we want to actually, another thing that we want to do here, oh, by the way, my apologies that the text is cut off here. I'll read it out so you know what it says. That was a mistake on my part. So one of the things that you want to do here is it's important when you're doing any sort of when you're thinking about security. Yes, you can design and add in checks, for example, to determine if, to prevent buffer overflows and that, but you still actually need to, just like you have to test for functionality correctness, just like you need to test performance requirements, you also need to verify that the software actually meets the security requirements. So this means that you have to actually test for security. And when we do testing for security, we actually need to think often a little bit more specific in terms of some of the techniques, because the traditional black box, white box methods, i.e. testing all the inputs, testing all the outputs, testing the requirements on the case of black box, or in the case of white box, doing tests for certain types of code coverage or data coverage, those tests often do not ensure that a software system is secure. They are insufficient. So what that means is that we have to think beyond just our traditional testing. And here's an example of why traditional testing doesn't always ensure that the software is secure. Let's consider black box testing, right? So black box testing is based on the software requirements. Security errors typically are often unintended program behavior, right? So it's behavior that doesn't necessarily, if you haven't built in security requirements, if they're not explicit, a security error is actually an unintended program behavior that doesn't necessarily violate the requirements for the software, right? This means that if you have black box tests that are designed around the requirements, they won't always find the security errors unless you've actually built in these explicit security requirements, which isn't always the case. It's becoming more the case now, but it isn't always the case in a lot of systems. They don't always think about the security side till later. So in this case here, because security errors are unintended and aren't always reflected in requirements, doing requirements-based testing at black box, in terms of black box testing, won't always find them. So let's consider now one type of testing that you can do that may find them. So one type of testing you can do is something called penetration testing or pen testing. And I briefly mentioned this when we talked about exploratory testing last time, because pen testing, just like exploratory testing, I would actually classify it as a type of exploratory testing. If you want to think about those as being different, it's still, both of these are what we call manual testing techniques. And in a penetration testing technique or pen testing, what you're actually doing is you're assessing the system's security by simulating or by doing simulated or mock attacks. So often what you have is you have the tester who takes the role of the attacker and thinks in an attacker's mindset about how they could essentially exploit a potential vulnerability and access the system. So in the sense of pen testing, though, you also still have a notion of what we call black box pen testing or white box. And the difference here, it's the same idea as with traditional testing, where black box, you assume the software is a black box and you have no knowledge of it. Or within white box, you assume that there's internal knowledge of the system under test. Pen tests based on black box often, that means they don't actually have any sort of knowledge about the security, about the versions of software that are running, or versions of utilities and stuff on the server. So what they typically will rely on when they do black box pen testing, where they don't have any knowledge of the system, is they actually often will start by utilizing phishing and social engineering techniques. So phishing techniques are, when you get those emails where what they will try to do is they'll try to get somebody who has existing credentials to click on a link where they will have a spoofed version of the page, which makes them think that it is a valid site, or where they can use those credentials, and then the credentials can be recorded by the attacker, and then utilize those credentials to gain access to the system and gain understanding and internal knowledge. So that's what often black box pen testing does. And the social engineering is sort of a similar idea as phishing, where instead of the phishing, the social engineering is really a little bit more, it's where they actually rely on sort of human weakness in terms of, for example, rather than just doing a generic phishing email, they might do a whole thing where they pose as a supplier, and they actually have conversations, and they get the person to think that they're the supplier, but at some point they're using a slightly different email that the person doesn't realize, and then the next thing you know, the person is sending this supplier potentially information or something, thinking it's somebody else. So that's sort of the social engineering side of this. Now, white box pen testing is a little different. White box pen testing relies on knowledge of the underlying system to make the attack. And this is common in open source software in particular, where the code may be available, they know the versions of things, and they can look through the code to try to find weaknesses. For example, find buffer overflow opportunities, ways to do SQL injections, that kind of thing. And again, simulate an attack. But this is done manually by somebody with considerable expertise. Any questions about this, about pen testing? So pen testing can be white box, black box, and is manual and requires expertise on the part of the tester. So another type of testing you can do for security is an automated technique called fuzzing. And fuzzing or fuzz testing, this is similar in some ways to what we learned about previously about shotgun testing, where we're trying a whole bunch of random values. The difference, though, is that unlike shotgun testing, where we are often trying a lot of the random values we're trying are valid inputs. In fuzzing, we're really focused only on the unintended or unexpected behavior. So we're really only interested in invalid or semi-valid inputs. So we're going to try a lot of interesting inputs that are not necessarily what the system would expect to be quote unquote normal or expected according to the requirements. So we're going to try things like, if there's a form, we're going to actually try for the first name, we're going to try long strings of characters, numbers, symbols. We're going to try putting code in there. We're going to try to do different sort of default values to see what happens. If we try something like, we'll try the name null to see if that actually fools the system into thinking something, because null is a keyword in the system. Those kinds of things. That's what we would do to try to see if we can exploit the system. However, unlike pen testing, which is focused, precise, with knowledge from the tester, fuzzing is automated, and the thing is, it's really brute force. So we try a whole bunch of unexpected automatically, and we throw a whole bunch at it, seeing if any of them will potentially break things. So I see a question here. Quick question, but if a website has a never-ending or a 24-hour session, could someone instead, regardless of having the password or not, use the token key to access the account? So you're asking a specific security question, and I get what you're saying. So in terms of the session information, that's something that would depend on the software you're talking about. I think a better question would be is, how would you actually test against that, right? And one way, that's something that you might try to exploit. You're probably not going to exploit that through fuzzing. that's something that might get exploited or assessed through a pen testing strategy. Okay, the idea of someone trying to access by potentially leveraging a session that hasn't expired, for example, I think is the example here. So that's something that could actually happen, right? Using a pen tester might try to use a public machine within the organization, if there is some that are available to guests or something like that, and see if they can actually utilize that to gain access. Okay, so that's a little bit about, I did pen testing, and now we're talking about fuzz testing. And I have a little more to talk about fuzz testing because I want to talk about, because it's automated, I want to talk about some of the different types of fuzz testing because there are different approaches you can do. And remember, I said fuzz testing is like shotgun because you're really doing large numbers of invalid or semi-valid inputs. So you're doing this at a large scale. So you need some strategy for how you generate the data that actually you will actually use to try to cause the unintended or unexpected behavior. So how do you generate data in fuzzing? Well, there are really three sort of strategies or three kinds of data. One of them is what we call black box random fuzzing. And this is what I said is similar to shotgun. And this is where you just simply generate large amounts of random inputs. There's no knowledge about the data format that's expected or anything. You're just randomly trying a whole bunch of different values. So you just think, you have some max range of number of characters, and then you know what the character set is, and you just throw random amounts of that character set on there and see what happens. Again, the difference between black box random fuzzing and shotgun is that black box random fuzzing is really focused on inputs that are semi or completely, I guess, that are unexpected or not normal inputs or not expected inputs. So they're invalid or semi-valid, I should say. Now, another strategy you can do is use what's called grammar-based fuzzing. And this is where you have insight, so you have an understanding of the valid data format, right? The input grammar. So you know, for example, there's a form and it only accepts 25 characters for the first name. It's supposed to accept this many up to this many characters for the next field. This field is of this format, and so on and so forth. So if you know that, what you actually do is you use that valid information to use mutation, very similar to the mutation testing we did, but where what you're doing is you're not mutating the source code like you're doing with mutation testing to create faulty software. Instead, what you're doing is you're mutating the inputs, the data, the test data. You're mutating it to create invalid or semi-valid from the valid data format. Okay, so you take valid data and you mutate it to become invalid or semi-valid and then try that. So that's the grammar-based approach where you have knowledge of the valid data format. The third type of fuzzing or fuzz testing is white box fuzzing. And this is where what you basically are doing is you have full access to the source code. And in this case, what you're trying to do is you're doing something called symbolic execution, which is where you're looking actually through the code and you're exploring the program execution paths using what's called a constraint solver. Don't worry too much about this, but the idea is that you're trying to explore all the paths through it and identify invalid or semi-valid data that will allow you to explore an unexpected path. And that's sort of what you're trying to do there. So symbolic execution, what it does is if you want to try to figure out a path, you can actually work your way back and figure out, okay, if we have two inputs, X and Y, X has to be, and you'll get an expression which represents a correct value of X, right? Maybe, and the same thing if there's a Y. And so what you're doing then is you're getting a representation of what value of X and Y will lead to some sort of interesting behavior. And then you try those inputs and see if you can get the abnormal behavior you expected. Okay, so those are three types of fuzzing. So remember, two types of testing: pen testing, manual, requires a lot of expertise. You take on the mindset of the hacker, it can be white box, black box. Fuzzing, completely automated, can be black box, white box, or grammar based, and requires a large amount of automatically generated data input to try to cause abnormal behavior. So those are the two types of testing we're talking about. Just to give you some examples in practice, I'm going to just show this here because I just want to point this out because this is like historical, but I think it's also relevant. So I remember seeing this back 12 years ago that Microsoft, this is when they first started using fuzzing at a large scale that I'm aware of. And they use what they call a fuzzing botnet. So they basically use this fuzzing tool on their Microsoft Office product at the time, and they were able to uncover more than 1,800 bugs. And what they basically did was they used the unused computing idling PCs essentially of employees to essentially launch this botnet that fuzzed Microsoft Office and uncovered all of these bugs. And they also fixed them all as well. So I think that's important to know. And all of the bugs may or may not have been security issues, but all of them led to unexpected behavior. So that means that not all of them may have actually caused a vulnerability in the software from a security perspective, but they all actually either were a security vulnerability or they could have been some unexpected behavior that was more considered a functional bug. So that's just to happen then. And then moving on more recently, and this was, we're moving on a little bit, 10 years later. I've got I said Google here. This is totally not Google. This is Microsoft. I just wanted to move on. My apologies, I should say Microsoft here. So that was what they were doing 10 years ago, 12 years ago. And then in 2020, what Microsoft did was they actually open sourced what they call the One Fuzz framework. And you can actually go and try this. And this is actually the framework that they actually are using. And it's actually under their Azure platform. It's an Azure testing framework. So they've actually open sourced this tool. So the point about this here is that this wasn't a one-off doing this back in 2010. They've been continuously utilizing fuzzing throughout, and it's actually something that is part of their process. Let me see, I see a question here. So there's a question here about if you tried to transfer essentially a large amount of money that would cause essentially an overflow, I believe is what they're talking, error. So a large enough number that would overflow if it was in real number int, whatever the size, and on an overdraft balance of -5 based on pre-existing knowledge, then this could in theory cause an overflow error. Would this be considered black box since we don't know the system, we just know the properties of integers and flows? So in this case here, so I don't know quite if you're referring to doing this in terms of fuzzing or in terms of penetration testing. You're thinking about in terms of penetration testing. Okay. In terms of pen testing, would this be considered white box or black box? If this is information that you can obtain from externally, right? So like, for example, if you're trying to get a username and you try a wrong username in the system and it tells you you try to create a new account and you enter a wrong password and it tells you all passwords have to be this information. That becomes, in my mind, that's public information that you do not have knowledge of the code to understand. So if you can gain the insight from outside of the system, then I would still consider it to be a black box. If you obtain the information by looking at the source code to understand the size limit, because right here you're making an assumption about the underlying, is it 64-bit, whatever it is, in terms of the variable type. So you're making an assumption here about the variable type. You don't know the variable type. So because of that, this would still be a black box pen testing. Yeah, if you're only, understanding common pitfalls and combined with external knowledge from the system that you can get without having any credentials, then it's still black box. Yeah. Okay. So that was about Microsoft and one fuzz. Here's the Google one. And so Google actually also has open sourced a tool called Cluster Fuzz. And you can also look at this. And they actually use this as well on all of their own products, such as Chrome. And they've actually used it to find 16,000 Chrome bugs. And they've used it on open source projects to find over 11,000 bugs as well. So I use these two examples because I want to show you that, you know, large software development companies like Microsoft, like Google, they take security testing seriously. They take security testing techniques like fuzzing seriously and have teams that work on this, develop state-of-the-art platforms for large-scale fuzz-based testing of their own products. And it's been common now for them to open source this and make them available, which is a good thing because I think you know, these tools are now accessible to their customers, to other people to try to use, and so on. So I think this is a good thing to see them contributing to the open source community. Any questions about sort of the Microsoft and the Google's use of fuzzing? I have the links here to this, and I will share those on the course website. So I'd encourage you to go take a look at these sites if you're interested in learning more. Okay, so in addition to testing, something else that you may actually be interested in is other types of what we call analysis of software. So in general, testing is a type of what we call dynamic analysis, meaning, and dynamic analysis is any type of analysis of the software system that requires execution. So testing is a type of, it's something we do. We test by running the code, right? We give it inputs, we see about outputs. So if we also were doing testing or we were doing some sort of analysis where we were monitoring the runtime and recording internal states of variables, that would also be a type of dynamic analysis. Now, there's also types of analysis you can do on the software without executing it, without running it, and this is called static analysis. And in the case of security, there are several tools you can actually do that are focused on security vulnerabilities and identifying security vulnerabilities through static analysis techniques. One example is something called spot bugs, and spot bugs used to be known as find bugs, and it's available. It's an open source tool. And what it basically does, it does a static analysis of your software system and identifies by looking at patterns in your source code. It looks and finds patterns that match known bug patterns. And if it finds those, it reports to you potential warnings about what you're doing. So it could, for example, if it noticed you in C++, and I don't recall if Spot Bugs does this, but it could, I think it runs actually on Java. So anyway, it could actually identify for you a potential pattern in your code that's consistent with a bug pattern. Does not mean you have a bug. It just means that you have code that looks like code that has a bug in it. So you get all of these warnings. Some of them are true. Some of them might be spurious, meaning that they're false positives. And then what you can do is you can go through all of these warnings and verify if they are bugs or not. So it gives you a starting point to look at. And it does this by analyzing the source code itself, not by executing it, which is why it is a type of static analysis. Another static analysis tool is actually from Synopsys, which is Coverity. And Coverity actually is a tool that assesses both, again, like spot bugs, does both quality and security analysis, and is something that you could also look at as a way to potentially identify bugs or static analysis, or sorry, security bugs in your code. So in summary, a lot of the testing techniques are really valuable. They can be supplemented with static analysis tools like these to give you more insight and other avenues to identify. So these types of tools aren't focused on looking at abnormal inputs and ways to find vulnerabilities. They're focused on looking for patterns in the source code that are consistent with known bugs so that you can find potentially vulnerable code and fix it. Any questions? Is security something that interests people? I'm just curious. Have you covered it in other courses? Okay. So this is a little bit of a high-level overview of security analysis or static analysis and testing for security. What I want to do now is switch focus a little bit and talk to you a little bit about a case study. And the case study I'm going to talk about is related to a project that I was on with some colleagues here at Ontario Tech. We worked with an industry partner, QA Consultants, which is a Canadian company. And we also worked with the Automotive Center of Excellence here at Ontario Tech, and as well as other partners across Europe and also in Canada. And this project was also funded in Canada through NRC. Now, I can't go into some of the specifics right now about about the techniques we developed quite yet. But what I can do is I can frame for you what the problem is and talk to you a little bit about cybersecurity in general. So what does anyone know, first off, what is a connected autonomous vehicle? Yeah, an autonomous vehicle is typically a car that drives what we know as a self-driving car. There are different levels. I'm not going to get into these, but there are different levels in terms of self-driving. So there are cars that are completely self-driving. There are cars that require, for example, a user to, essentially to be there to monitor, to have their hands on the wheel in case a problem arises. There are also self-driving capabilities in a lot of today's vehicles, such as lane correction, crash avoidance systems, where the vehicle will take over and take evasive measures, but does not drive in the majority of situations. So there's a whole sort of gambit of possible different, I guess, levels of autonomous vehicles. And then the connected part of this is really talking about the fact that these vehicles aren't just autonomous, and are closed off systems. They are connected. They're connected, via wirelessly, via Bluetooth, via other networks to devices in the vehicle, like your phone. They may be connected to satellite data coming in about GPS or something else. They might also be connected to other connected vehicles in the same environment. They might be connected to infrastructure that is in the place you're driving. So they could be connected to smart street lights, signs, that kind of thing as well. So there's a whole array of different devices that a connected autonomous vehicle might be connected to. So when we talk about CAVs, we're really talking about vehicles that use sensors to detect the environment and ideally operate without human input. And the other thing is, when we talk about the connection part, there's a whole bunch of vehicle communications that can happen. There can be vehicle to infrastructure. For example, infrastructure could be things like traffic lights, like I mentioned. There's vehicle to vehicle, which means a vehicle communicating with another vehicle on the road. For example, a vehicle could communicate to a vehicle behind it that there's a traffic accident up ahead. There's vehicle to device. This is looking at things like connecting to my phone in the car. There's vehicle to pedestrian. So vehicle may be connecting with devices that are with the pedestrian, right? So it detects a local smartwatch to could send out a signal about the location of a pedestrian in a crosswalk. And if the vehicle picks up that signal, it actually knows to brake automatically because there's a pedestrian there, even if the cameras or sensors didn't detect it. And then there also is vehicle to X, which is really, I forgot vehicle to network, where they connect to wireless networks and so on. And then there's also vehicle to X, which is to any internet-enabled device. So this is like the whole Internet of Things, smart devices. And yeah, so there's all of these different things that can happen, and all these different types of communication that happen when you have connected vehicles. So how does this relate to cybersecurity? Well, the work that we were looking at was actually so we had two parts to our project. One of them was we were actually looking at pen testing, different aspects of the vehicle. That largely wasn't what I was involved in directly. I was more involved in the low-level system anomaly detection or attack detection within within the CAN bus, which is essentially a controller area network, often known as the central nervous system of the vehicle. And the CAN bus, this is actually how all of the electronic control units in the vehicle communicate with each other. And the ECUs you can basically think of as computers, right? These are the individual units. They're computers for different things all throughout the vehicle. It could be for the ABS braking system. There might be one related to, well, it could be one related, you're talking about the infotainment system as a computer. There might be one related to engine, right? And so on and so forth. And it turns out these ECUs are somewhere in the range of 50 plus in a typical vehicle. So CAN is the bus where all of these communicate with each other because these all have to work in tandem, right? The ABS doesn't just kick in on its own. It actually does so because of communication from some other ECU, which has sensors connected to it, which identify things like the brake pedal was pressed, or it could be it automatically comes on because it detects, in the case of an autonomous vehicle, through LiDAR, that there's an object immediately in front, a pedestrian, a deer, another car that has suddenly come in front of the vehicle. So this is sort of what we're looking at here. And the case that we're looking at is we're looking at this case where an attacker exploits a vulnerability to gain access to the CAN and then either control one of the ECUs or potentially spoof messages as if it is one of the ECUs. So it either fakes being an ECU or takes control of an ECU. It sends out erroneous messages which cause the ECUs to act in unexpected or unintended ways. And because these car systems are connected and the number of connections that exist, these systems are more vulnerable than ever. And the types of attacks can be a whole bunch of things. So you might think of like this picture here where there's somebody actually trying to connect in, right? Well, some attacks actually require physical access to the vehicle, right? There's something called an OBD port underneath in the wheel well or in the footwell of the car under the drivers where you can actually connect in a device and connect your computer to the car. That's often where when you've seen things like insurance companies put on monitoring software in exchange for lower insurance rates, they're connecting into that port. But it's also the port that when you bring your car or bring a vehicle into a garage to get diagnostic information, they hook up the diagnostic computer there as well. So if an attacker has physical access to the vehicle, they could actually try to connect through that. They could also try to connect through, if they're in proximity to the vehicle, but not necessarily directly physically connected, they could also connect through something like the Bluetooth. They could also connect through the wireless network connection, right? They could also do it somewhat passively by, for example, all of these cars have to get updates, right? And these updates often happen over air automatically. Sometimes I'll see a little symbol on my car because I know there's an update coming in. And one thing they could also do is they could also break in to the server. So maybe the vehicle is hard to break into. So instead of breaking into the vehicle, what they do is they attack the server, the update server. And then what they do is they inject some code into the next update for the vehicle. And that injected code either causes some behavior to happen on its own, so some sort of automated attack through the inject, or it actually causes some sort of exploited vulnerability, which allows a backdoor into the vehicle for an attack to happen. So that's one example of something that can happen. So there's, and I'm not trying to scare you from driving in, autonomous vehicles or vehicles in general, but there are a whole bunch of ways and things you have to think about, right? Also, a lot of these ECUs are developed sometimes by what are the OEM manufacturers. So there's, the car manufacturer doesn't build every single component. They actually have they use components from other companies that maybe only do certain types of systems. And somebody might also exploit the software in one of those ECUs at, when it's under development, so that the actual software that the ECU ships with has a vulnerability in it from day one, right? You also have to think about challenges when you're using standards, like I mentioned Bluetooth earlier. Well, there are actually potential exploits in Bluetooth. So depending on the version of Bluetooth, they may be trying to utilize a known vulnerability in the Bluetooth, right? Now, here's a good thing about that is that the Bluetooth is through the infotainment system. And many vehicles, the infotainment system, because it actually is what you typically connect your phone to and other devices, they restrict the infotainment system's access to be able to connect to the CAN bus. So they may have it set up so only data can only be received by the infotainment system, not sent from the infotainment system to other components. So there's a whole bunch of things that can happen here, but there's all kinds of ways these vehicles can be exploited. And these all have to be thought of and worried about by the car manufacturers. So what we were doing in this large project is we were actually doing something called variant testing, and the name of the project was Shift, Excellence in Variant Testing. And we were really interested in ways we could better support testing for different types of bugs, including security bugs, across a number of different industries across product variants. So in the case of automotive, the variants are all of the different vehicles in the vehicle lineup that a manufacturer has, right? So every different model of car is a variant because they all have some overlap in the systems, the software they're using. And then within each vehicle itself, there may be variants in terms of different versions of the vehicle with different combinations of features. There also may be variants across different regions where, because of regulatory differences and so on, certain vehicles may have slightly different software, slightly different components in one country from another country. So there's a whole bunch of variants that we're dealing with here. And we were looking at this problem of how do we actually help support cybersecurity testing for vehicle variants, essentially. Okay, so that's sort of what we're doing. And like I said, the work that I was doing was really focused on detection of attacks. And just so you understand here, what's the CAN? Well, CAN actually, just like you think of on any network, there's actually a message frame or sort of a packet format, right? You'd see this if you're dealing with the internet. You see this when you're dealing with all kinds of different types of networks. So every message on a CAN, in the CAN, has this format. I'm not going to go through all of the different sections here or different flags and so on. I just want to draw your attention to the three blocks in color. There's what's called a base ID, which is an ID message, an ID for the particular CAN message. So that a message can have a particular ID, right? So and that really tells you what kind of message it is. And then there's an extended ID, and then there's data. The data contains information that's being sent from one ECU to another, such as it could be vehicle speed, temperature of a certain component, presence or absence of objects that are detected by a sensor or a LiDAR is connected to the ECU, that kind of thing. And what I will mention as well is that in most what we consider to be just standard passenger vehicles, the extended ID is not utilized. It's only the base ID plus the data, okay? The extended ID, though, is there because this format, it turns out that passenger vehicles are not the only vehicles that actually use a CAN. And other vehicles use CAN, such as industrial tractors, cranes, large trucks, that kind of thing. And a lot of those vehicles have additional functionality which requires them to utilize the extended IDs as well as the base IDs. So that's a little bit about that. The other thing I'll mention is that the base ID has a priority. The lower the ID, the higher the priority on the network. So messages that have a higher priority have lower ID numbers, okay? And every ID has, in a vehicle, will typically have a standard. So the data packet is encoded, but in that encoding are a number of different signals. Each signal is corresponding to some data point that is being communicated with that ID. And the signals are often encoded themselves. So for example, they may not be actual values. It might be that they encode a value here that you then have to plug into a formula to get the actual value you want. So they're all encoded in here. So signals encoded in data. Data corresponds to the base ID. Base ID are prioritized with lowest base ID has highest priority. Okay, so that's pretty much what you need to know about these CAN messages in vehicles. And here's the interesting thing. So what we were interested in doing, and we actually started with, and I have the link here and you can go check it out. There's a car hacking data set, which is from the Hacking and Countermeasure Research Lab in Korea, South Korea. And we utilized this data set that they actually got from a Hyundai vehicle. And we utilized this for some of our initial work before we actually investigated things like connecting to a vehicle directly ourselves to try to get our own data. So we started with this, and the format of this, I'll kind of go through it so you understand what you're looking at here. The very first thing to know is that the data has a timestamp. So they actually connected into the OBD port, and they injected data, attack data, and they recorded all of the data, including the attack messages, along with the timestamp. So the timestamp tells you when a particular CAN message was sent. And so we get all the messages in sequence along with the timestamp. So you can understand things like the frequency, the timing difference between messages with the same ID, and so on. The next thing for a given message, each message corresponds to a single row, is that the message has the CAN ID, which is the base ID. And if you go back and you want to go back and look at the base ID that we talked about, the base ID was 11 bits, right? So 11 bits, if we go back here now and look, that essentially corresponds to, you can represent 11 bits in 4 bytes. So that's what we're looking at here. It's the 0, 0, 0, 0, sorry, 4 zeros. That is a CAN ID. 0130 is a CAN ID. So it can represent numbers from 0 up to the maximum value that can be represented by 11 bits. And that's what's recorded here in 4 digits. The next thing that's recorded that they have here is, if you look at it, is the size of the payload. And this corresponds, the payload is the data that we talked about. So here we're talking about 8 bytes of data in the payload, okay? And then the next thing you actually see is the contents of the payload, okay? And this is where we actually have every byte represented separately, okay? But together, and they're all represented in hexadecimal format, okay? Questions? We're good? Okay. Then the very last thing here is a label. And this is important because the label actually allows us to determine the difference between a real message and an injected message. So they actually label messages that are from the system, so that are generated by the vehicle, and label the messages that they actually attack. For example, let's consider an intrusion attack, which is what I was just showing you. So an intrusion attack that's of one type is called a denial of service, right? So what does a denial of service do? It actually tries to essentially flood the system with a whole bunch of messages to delay other messages from getting processed in a timely manner. So what this would do, for example, in a self-driving car is delay real messages, for example, about the presence of a pedestrian or objects to avoid hitting or that kind of thing. It will delay those real messages from being received. And the way you would do a denial of service and the way they did it was they actually just rapidly, every 0.3 milliseconds, they injected into the system a CAN message with empty data and the ID 0000. And all of the messages that are marked with a T are the attack messages, and the R messages are the regular messages, the messages that the system is sending itself. So why would they have chosen the 4 zeros as the CAN ID here, do you think? Why not choose some other number for their denial of service? Well, priority, right? Yeah, to place it on. So remember what I said. These IDs, the CAN ID, when these messages are received by an ECU, they are prioritized based on the ID number. Lower IDs get higher priority. So by giving it the lowest possible number, they're really trying to do is flood the system with high priority messages, which will have the most impact. If they gave it a higher number, those wouldn't lower number ones would be prioritized, and the system may not actually have as much of an impact. So by doing this, they're trying to maximize the impact of their denial of service attack. So that's one type of intrusion that you could have in these vehicles. Another type of intrusion that you could have in these vehicles, and I realize I'm totally going to be cutting off some of the data, but is a fuzzing attack. So it turns out, remember I said fuzzing data is something you want to do? Why do you want to do fuzzing? When we do fuzzing as a testing method, why do we do it? To try to see if we can create abnormal behavior to correct. Well, it turns out that an attacker may also want to use fuzzing as a technique because it can lead to the creation of abnormal behavior, but they're doing it because they don't want to fix it. They're doing it to actually cause something to go wrong in the system and to trigger unexpected behavior. So it's using the exact same method as a tester would, but for a nefarious purpose. And in the case here with fuzzing, what they're basically doing is they're injecting real messages, right? So messages with just standard IDs, and then but what they're doing is they're putting in random payloads, okay? And there's different ways you could do this. You could just be creating random ID messages, right? Random IDs and random data. You could also be watching the system. When you see certain messages come in, you basically observe real messages and then you just recreate the same ID with different random data to mess the system up, right? So you could actually use it as a way to sort of create random fuzz data for legitimate messages that are sent around that time in the system. But in any case, these are two different types of attacks. And then there are other types of attacks too, which can be more nefarious. So even further, so what I could actually do as well is if I know what a certain ID message is, I know it's related to a certain behavior, I could actually target a certain message ID type with certain data. So like, for example, I could take real data, decode it, get the signals, change a signal, re-encode it, and pass that along to give it real incorrect data. So for example, I could change information like, like I could go in and if there's a message about an object, a car in front of them, I could change it so that I could adjust the distance by doubling the distance. or making it think the car is twice as close, so slam on its brakes, or those kinds of things, which is obviously not good, and that's what we're trying to prevent in our case. So these are examples here of some of the attacks that can happen. And the kinds of things that the questions we're trying to answer here is, I'm not telling you this because I want to give you a crash course on how to go and hack your car. I'm telling you about this because I want you to understand and appreciate the challenges that go into testing and providing confidence in the security of a vehicle. So what we were interested in this case is we're interested in things like, how do we detect attacks? How do we test vehicles and ensure that they're resilient while under attack? Because part of it is, how do we prevent them, right? How do we test for security vulnerabilities, find them, and fix them? But assuming vulnerabilities can still happen, how do we actually make sure the vehicle is resilient to attacks? And these are all questions we were exploring in this SHIFT project. And specifically, and as I mentioned, I'll just tell you a little bit, the SHIFT project was actually part of what's called an ITEA 3 project. And we have 21 partners, 5 countries, and I believe, and it ran from September 2018 to December 2022 is the end date. But technically, that's the end date. But we actually wrapped it up roughly in January is when we wrapped it up. So in any case, that's that project, and that's what we were working on. And I'm happy, if you want to check it out, you can go to that website, shift.org, xift.org. And specifically, what we were working on was a specific use case. And the way it is that there are different research institutes in this, and research organizations and universities in this project, as well as industry partners. And several of the industry partners, a number of them, they actually brought use cases into this. So one of these was from a German automotive company called Explio, and the use case they brought was, consider the fact where you have a pedestrian detection system or an advanced driver assistance system, whatever you want to call it. And the idea was to help them avoid catastrophic collisions. And in our case, we were interested in trying to ensure that we could actually detect and identify potential attacks towards the pedestrian detection system in the vehicle. That's what we were focused on. And we did this largely through utilizing machine learning techniques to try to identify the difference between normal and abnormal CAN ID messages, so that we could identify things that are abnormal, which are more likely attacks. Because with these attacks, there are known types of attacks, like I mentioned with the denial of service or with the fuzzing attacks. There can also be hybrid attacks where they use some combination, right? A whole bunch of denial of service messages plus random data. You could also have targeted attacks. You could have attacks which spoof a real ECU or take it over and send out nefarious messages that are just slightly off in terms of the data. You could have a whole bunch of things going on here, and you can't always predict every kind of attack. And you need to be resilient to unknown attacks as well, which is why we focused on telling the difference between abnormal and normal behavior rather than detecting attack X, Y, and Z. Okay, I hope you found that interesting about the connected autonomous vehicle cybersecurity. There wasn't as much testing in it, but I did want to give you a sense about some of the real challenges that could be faced in the research environment, as well as in industry, when it comes to security testing and keeping systems and devices secure and software secure. The other thing that I will just mention as a final wrap up to this is that while I'm done on this project officially, I'm still actually doing some work related to this and related to analysis of these types of messages. And if anyone in the class is actually interested in this area for a potential honors thesis next year, feel free to reach out and send me a message, and I'd be happy to talk to you about it more. So, in summary, what we've talked about today is we've talked about the role security has to play as being part of quality. We've also introduced testing, primarily penetration or pen testing and fuzzing, as well as security analysis as 2 complementary general strategies or approaches to identifying security issues in software. And we looked at a security case study where we did a little bit of an in-depth dive on connected autonomous vehicles and the challenges with detecting attacks and being resilient to attacks that happen at the low level of the CAN bus. If you're interested in more, I actually have an interesting paper here about fuzzing by Patrice Godefroy called Fuzzing, Hack, Art, and Science. And I'll put this up in the links as well on the website. But this is an interesting, if you want to know more about fuzzing, this is a great article to give you a bit of an overview. And lastly, I just want to acknowledge and thank the Shift partners who contributed to the background content for today's talk. And in particular, two students who did work on this project in my lab, Naida Tanya, who you might know, who's a fourth-year student, as well as Michael, who's also one of our fourth-year students as well. So both Naida and Michael, they both actually worked on this, each of them for one summer, and Michael has kind of continued to work on this throughout the year, a little bit part-time. So I just want to thank both of them for their work on this. So that's Naida, Tanya, and Michael Liu. So, okay, great. So thank you very much for your attention. I'll stop the recording now, but I'll stick around for a few minutes if you have any questions.